All right, so today is I'll finish up the last two lectures that are covered before exam 2. And homework 19, covering today's lectures, due Friday. And after you do that, you'll have done all the homework on the material that's going to be on exam 2. And you can start studying for the exam by first doing the study guide, and then grade yourself with the key. So I really advised you to do this before the practice exam, so I'm going to wait till tomorrow to post the practice exam and the key. And all the homework that is covering exam 2 material is now, except for homework 19, of course, is now posted on Kappa. So any homework problems that you had difficulty with, I suggest you go back and retry them. And a lot of them you can randomize and you'll get new numbers each time. So it's a great way to practice some of the stuff you're rusty on. And so again, in office hours, I just want to remind you, Thursday office hours are midday here. They're not late afternoon. So come by if you need any help. All right. Now, let's just go to the document camera, and we're now going to cover chapters 40 and 41 today. So in chapter 40, what we're doing is we're going to look at Z and T tests for pairwise comparisons. So once we've done an overall significance test with chi-square and F and rejected the null, that all the group means are the same, and found at least one of the groups is different from the others, how can we determine which pair is different? If we know at least one, it might be all of them. So we want to test them all. So that's what we're going to look at now. So we're going to continue with that example that we were looking at before on page, we started it on page 178. I'll just refresh your memory here, where we were asking, this is data from 858 stat 100 students, and on their opinion about gay marriage. These are the people who strongly oppose it, all the way up. If you rated it as 10, these are the people who strongly favored it at 0. 10 means you strongly oppose it. So we looked here and we said, okay, this is our results. We're looking at 5 groups. We wonder if there's differences among different ethnicities about this opinion. So we looked at this and we saw the 5 averages here, and we noticed that which one has is most strongly opposed was here, right? And we saw which one most strongly favors the lowest average is here. So that's the biggest difference we saw, right? But there's we'd like to look at all the differences between all the groups, okay? So let's go back here and said, okay, so if we want to, how many possible pairwise comparisons are there with 5 groups? So let's think about that. How many, for 5 groups right here, how many pairwise comparisons are there, unordered ones? So, for whites right here, if you compare whites, you can compare them to 4 other groups. Blacks, you can compare to 4 other groups, etc. So for G equals 5, for groups equals 5, it looks like there's 5 times 4 pairwise comparisons, because each of the 5 groups can be compared to 4 other groups. But then we want to divide by 2, because we don't care whether we want to count white versus blacks as the same as blacks versus white. We're not ordering them. We just want to look at the difference between them. So that it would be 5 times 4 divided by 2 pairwise comparisons. If we don't care about the order, that's why we're dividing by 2 here. Otherwise, it would just be 5 times 4. Okay, so for G in general, for G groups, the number of comparison is G times G minus 1 over 2. Okay, so you can look at these right here on page 184, and you can see what I mean. So here's the 10 comparisons right here. This is 10 comparisons. Okay? Does that make sense to everybody? Okay. So now, let's say we saw that big difference between here's the blacks had the highest average and the Hispanics had the lowest. So why don't we just look at that? Let's start by comparing the blacks and Hispanic averages to see if the difference is significant. Now we just have two groups, right? So we can just do our usual Z or T test. Why don't we use the T test? Okay, because that's what's normally done in this situation. So our null hypothesis would be what? That even though we see differences in the averages in our sample, we have to imagine a larger population that we randomly sampled these total of 858 students from. Because clearly there's differences in our sample, but would they hold up? Like in the next class of Stat 100 students, for typical Stat 100 students, are these differences significant or not? That's what we're looking at. So our null hypothesis is the usual one, that in the population, that's why I'm saying mu for the blacks, the mean in the population, the whole population of possible Stat 100 students or typical Stat 100 students that we're assuming these 858 were randomly sampled from, that there the population between blacks mean and the Hispanic mean is the same, that there's no difference. No difference in population means between the two groups. We just happen to see one in our sample just due to random variation. That's what the null always is, that whatever effect we observe in our sample is just due to random variation. And the alternative always is null, that it reflects a real difference in a wider population. So this would be that they're not equal. And we're just going to say not equal, just two-sided. Okay, two-sided alternative. So now we're just going to do our usual T, and remember that most of our significance tests just have some observed difference in the numerator. It's minus some expected difference. Certainly when we just are looking at one difference, we don't have to square anything. It's always the observed minus the expected difference. You don't have to square it. You just have one single number up here over the standard error for the difference. And because we're doing a T, we're going to make that adjusted standard error. Standard error plus. We're going to adjust that. Okay, so so far it's pretty easy. We just look at this difference here of what? What is the difference between the two averages? Right here. So that's 3.643 minus 1.848. That's what the numerator is. And the denominator, we have to remember how to do this standard error for the difference. So let's turn to the next page. We had this before, and let's just review it. It's going to be slightly different this time. So let's go to the next page and look at this. I know it looks sort of overwhelming here, but you'll understand it in a minute. Okay, so this is what we did before. When we were looking at, we were trying to combine two standard errors from two different samples. Here we have from the standard error from the black sample and the Hispanics, right? And the general thing is to use basically this Pythagorean theorem, right? you combine these, the standard error from one, let's say from A, and from B, we did this before just with our two samples z-test, and say the way we combine them is by, this is the standard error of the difference, is by the square root of the sum of their squares. So this is bigger than either one of them, but smaller than the sum of them. Okay, so we've done that. And then if we're doing, this is for a z-test, for a t, we just make those a little bit bigger by dividing through by n minus the number of parameters. You're used to n minus 1, but now we have more parameters, okay? So that's what we've already done. Now, the F and chi-square test make this assumption about equal variances. That's one of our three assumptions. That, remember our three assumptions about the errors was that they're independent, right? And that they have equal variances and they're distributed normally. That's often written IID, independent, identically distributed, normal with zero mean and the same variance. So we have this, I think that's a page we skipped. We can just check on it. I'll show you where that comes from. So we can go back. Right here on page 180. Those were the assumptions for ANOVA. They're the same as for regression. So there's nothing new here. Same as for regression. We've already had this. And independent, here's those three assumptions about the errors. Independent, and here's normal, and here's the variances are equal. This is the one I'm talking about, okay? So we have to assume we're assuming that's true with ANOVA here. So let's go back. So we're going to adjust our standard errors a little bit. Okay. So we assume this is number 3. Assumption number 3. Okay, it's what we've always had. Now, so this means we have to estimate the same standard deviations for all the groups, even though our sample standard deviations will vary somewhat. If they vary too much, then we can't do ANOVA. We have to do something else, and you can see we're going to do a re-randomization test. That's something else we can do. So let's check and see how much they vary. And it's sort of just, we can look at them. So we look at these standard deviations, and they don't seem like they vary that much. There are different rules about it, but we're just going to look, for this class, we're just going to say, hey, they don't vary that much, these standard deviations, right? So we're actually going to use this right here as an estimate, as a pooled standard deviation for all these. So let's read about that. So we average all the squared standard deviations. We do a weighted average by their sample size. And we use the squared, we take the square root of it, the square root of the weighted average, and that's called a pooled estimate. A pooled estimate of the standard deviation of the population instead of and in fact, that's what the standard deviation of the errors are. They're a pooled estimate of the standard deviation of the whole population. Okay? So we're going to use that instead of these two separate ones. All right? In our formula. So here's how our formula is going to change. So we can just look at it here. So instead of using this, right, we're going to use the pooled one. We can jump down to this, because this is the one we're going to be using generally. Okay? So instead of taking the square root of two different of Hispanics and Black standard deviations, right, instead of doing that, we're going to use this pooled standard deviation of the errors for both the Blacks and the Hispanics, right? And then, remember, standard error is the standard deviation divided by root n. That's what we always do for the standard error of a mean. Remember, we're talking about means here, the difference between two means. And the standard error of the mean is always SD over root n. That's all we're doing here, right? But since these are the same, we can factor it out, right? Factor out. Now you have the square root of the SD plus errors squared, so we factored it out here. And that is our formula right here. So it's actually pretty easy. But I want you, you're not going to have to derive all this, but you will have to know it. So this is one that's not going to be given to you, and this is the one you're going to be using. Okay? So no for exam 2, because you won't, unless you want to go through this derivation. It's much easier just to remember that. So this is what our t-test is going to look like. All right? So let's go back and do it then. So here we are. So that's our numerator right here. And you're always going to be given that, right? You're always going to be given that. So let's remember the standard error plus for the difference is just going to be the standard deviation of these right here, 3.180. And then, remember, you always have to divide through by the square root of n, but we have two n's here. Here's our two n's, one for blacks and one for Hispanics. So we're going to divide through, put the square root of 1 over 84 plus 1 over 99. So that's what it looks like. Okay, so it's pretty easy to do. That's what we're going to be doing. And then, of course, this difference, you just subtract these two right here. And this turns out to be 0.4717. Okay? And so I got a t-statistic of 3.804. Any questions so far? All right, now we have a t-statistic. Remember, for all the they're a series of curves. How many degrees of freedom do we have here? So, how many degrees of freedom? Remember, the degrees of freedom is always going to be equal to n minus the number of parameters, right? And for here, that's for groups, it's n minus g. So it's just equal to, it's the same as, right here, the degrees of freedom error. We're using this right here, so it's going to be the degrees of freedom right here for the errors. We're using this, that's a way to remember, so it's going to be the degrees of freedom n minus g for the errors. 858 is our sample size minus 5 groups. Remember, we did that for slopes, too. It was n minus p. Remember when we were looking at individual slopes in multiple regression? So remember, g and p are the same here. It's the number of parameters. All right, so we've got that. So now we're just going to do our usual thing. We'll look at a t-curve. And we'll have to look at the one with what? 853 degrees of freedom. So this is t. This is a distribution. 853 degrees of freedom. And when the null is true, we're going to have, both a slope, a difference of 0. This is an expected difference of 0 when the null is true. And this is a 0 as a z-score. And as our expected difference. Now, what expected difference did we get? As a z-score, we got this, not 0. So we'll have to, that's what we're trying to figure the p-value for, but it's two-sided. So we're looking at between 3.804 and negative 3.804. And we're going to look at both sides. Why? Because we're just doing an unordered, we're just looking at that comparison. We just think there's a difference here. And that's what we're going to do. Okay? So, what do we get? We get, when I did that, I got a p-value. it's really tiny, equal to 0.0152% in the two tails. Now, we've got to think about, now we're going to have to do something with this p-value. We're going to have to use the fact right here that there are, what? 10 pairwise comparison, 20 divided by 2. And we just looked at the first comparison right here, but we're going to be looking at, if we look at all 10 of them, we have to adjust this p-value. We have to, if we just looked at one of them, and we hypothesized ahead of time that there's going to be a big difference between blacks and Hispanics among all those groups, which I certainly wouldn't have hypothesized. I was very surprised by this. I didn't know which groups would be different. I really couldn't say. So I really was going to look, I wanted to look at all the groups. So that's what the printout does here, right here. Looking at all the groups and computing t-statistics for all of them. Now let's look at what happens to this. Remember, let's keep in mind our p-value that we got right here. This one of 0.0152%, and let's look at it here. Let's look what happened here. Okay, so we're looking at the blacks minus the Hispanics here, right? So this is the difference we got. Didn't we get that right here? We got this is the difference in averages. That was our numerator. This was our standard error. We just computed that. We divided the two and we got this. But why is our p-value 10 times bigger here? So this is just what we got, remember? Right here. So you know what this is right here? This is our usual p-value that we just computed times 10, because there's 10 pairwise comparisons, right? Our usual p-value, which was 0.01523% that we just computed, and we're multiplying it by 10 because we're multiplying it by the number of pairwise comparisons. And in this case, that was 5 times 4 over 2, which is 10. So what that's called is the adjusted p-value. And notice these are all multiplied by 10. That's why they're so big, like 100% p-values or more. It doesn't go over 100%. Okay? So because we're looking at 10 comparisons at once, you see, this is exactly what we did here. I'll just write it here again just so you can see. So this was the difference, 3.643 minus 1.848. That's this right here. And this part right here, 3.18, that was this that we did, just putting it together to make sure you remember. So the numerator gave us 1.794 right there, and the denominator, this part, gave us that. There's just so many numbers, I don't want you to get confused with all these decimal places. Okay, so this right here is just that, and then we have this. And then when we did that, we got a t-statistic, exactly like what the printout says, of 3.804. And that's that. But then our p-value that we got was 10 times less. And I'm saying, why are we multiplying by 10 here? Because we're using something called the Bonferroni correction. So let's read about that. This is we must use the corrected p-value. And we're going to do the Bonferroni one. There's other ways to correct. The Bonferroni corrected p-value when when you compare multiple, when you make multiple pairwise comparisons. You have to multiply it by the number of comparisons. So let's read about that and why. The p-values are all multiplied by 10. Why? It's because we performed 10 tests and didn't specify which of the 10 differences we'd expect to be significant beforehand. We looked at the data and did something called a post hoc comparison, an after looking at the data comparison. So the idea is that if you're going to be looking at, think about it this way, what is the p-value? The p-value is the chance that you'd see such an extreme, we're expecting 0, that you'd see such an extreme difference like this of 3.804 just by the luck of the draw. So, but if you looked at, imagine looking at 100 of those, doing it 100 times, 100 pairwise comparison. At the 5% p-value, that means 5% of those 100, 5 of them, you would expect to be as extreme. You'd expect 5% of them to be statistically significant just by the luck of the draw. It's called, so we have to avoid cheating like that, data snooping or p-hacking, like we talked about before, you have to make an adjustment to your p-value by how many comparisons you had. Remember, if you ran a whole bunch of experiments, trying to detect some effect, and you did it over and over and over again 100 times just by the luck of the draw, 5 times you're going to get, that's what it means. On the average, you'd get five of those experiments, you'd get significant results. So you can't cherry pick, look over the experiments and say, hey, I found significant results, so that means I'm going to reject the null. That's cheating. So in order to avoid that, you have to correct your p-value. So here's the mathematical explanation that we have 10 comparisons that we're testing, and it shows what the actual, if we set our significance at 5%, then what's the probability of getting this on page 185? And you're not going to, I'm not going to ask you to do these calculations, but I think it's useful to understand them. So if we set our significance level at 5%, what's the probability of getting at least one significant difference just by the luck of the draw when the null's true, right? When there's really no difference in the population, they're all the same. But in our sample, just by random luck, what's the chance that we're going to, in our sample, they're not going to be exactly the same, and what's the chance of getting such a big difference? Well, we can use our probability rules. The probability of at least one significant result is what? The probability of at least one is 1 minus the probability of none. We know that. So that would be 1 minus the probability of none is going to be, the probability of 1 is 5%, the probability is none is 95%, 0.95, right? But if we're doing 10 of them, it's going to be raised to the 10th. So that's 1 minus 0.95 to the 10th, which is equal to 0.4 or 40%. So with 10 comparisons, we have a 40% chance of making a type 1 error, a false positive, and rejecting the null when the null is really true. So it's really equivalent to setting our significance level at 40%, not 5%. So whatever your significance level that you set is, the Bonferroni correction divides by the number of pairwise comparisons, okay? So let's just check what we do. So if we divide by 10, what happens? So now we have 10 pairwise comparisons, right, at alpha equals 5%. So now our adjusted Bonferroni p-value is really not 5%, but what is it? 0.5%. So now if you do the same calculation, at significance level 0.5%, let's do the same exact calculation, you end up with, just doing the same exact thing, you end up with very close to 5%, but actually setting the significance level 10 times smaller. The idea I really want you to get is just that you have to be very careful and understand what this p-value means, and you can always find significant results if you do enough tests. And so we have to correct against that cheating, which is, you'll read, if you hear about p-hacking all the time, and data snooping, and ways people cheat, and it's very hard to guard against it. So I just want you to be aware of, this is one method to do it, okay? It's a very conservative method because it assumes in these calculations independence, that the pairwise comparisons are independent, and they're probably not. But it's a very conservative way and very simple way to understand. So that's the one we're going to be using. And let's see. All right. So here's our summary of what we've done so far. And we said in this chapter 40, and what are we saying? We didn't talk about this. Okay, so there's basically two ways. Once you do an overall significance test and find that at least one of the groups is different, then we proceed with these individual t-tests, okay? We did the same thing with slopes. We did the overall, in multiple regression, we did these F and chi-square tests to look at the overall effect, the collective effect of all the slopes together, the whole pattern, right? Now we're doing the same thing with groups. It's a special case of regression, okay? We're doing exactly the same thing. Now, when you want to look at the individual slopes or you want to look at the individual pairwise comparisons, then you do Z and T tests, and we're focusing on T tests here because that's what's generally done. So now there's two ways to do this. If we single out which group mean will differ before looking at the data, then you don't have to use any kind of correction because we're saying ahead of time, we're singling out one test. We're not going to do multiple tests. We're saying we think it's going to be this one ahead of time. Like the next time we did this, we might single it out ahead of time. We say, okay, we're just going to, now that we know it's going to be a big difference among those two ethnicities, the next time we can make that hypothesis and say that's the one we're looking at, okay? Then we don't have to do any kind of adjusted. We just do a regular t-test. But if we single out after cherry pick, pick out data snooping, or there's two ways. There's either if you do that, if you single out after, that's called post hoc comparisons. That's the title of this chapter, after this post hoc, okay, after looking at the data, or do significance tests on each of the G times G minus 1 over 2 possible pairs of group mean differences, then you need to use this correction or some other corrections. There's other ways, but this is the one we're learning. And here it is. So this will not be given to you, and you have to know this. And what does it do? It reduces the probability of making a type 1 error, of claiming it's 5% significance when it's really 40% of the time you're going to see a difference that big if you look through all 10 comparisons. Okay? So that's the idea. Now, let's see what else before. Any questions so far? You're not going to ask to do these calculations, but you do need to know this. And so why don't we do an iClicker right now? Okay. Okay. So here, I'm just asking you, if you have 4 groups, just how many pairwise comparisons are there? What would you have to multiply your p-value by? with 4 groups. Just make sure you know how to do the calculation. And remember it, mostly to remember it. Okay, did everybody get a chance? Just answer. You know, we're just doing participation here. Just try to get the right answer, but just make a guess. Okay. And let's see what you said. The answers. What happened? Why didn't I? Anyway, I can't. I must have. It jumped and I can't. I don't think I can. Can I see? Oh, yeah, I can see. Great. Terrific. Terrific. That's right. 4 times 3 over 2. Terrific. I hope you remember it. All right. Let's see what the next iClicker is here now that we're here. Let's see if you can answer this. Okay, this is a good one too. All right. Read this carefully, all the choices. I'll give you a moment to read it. Okay, did everybody have a chance to look at this? The answer right now is what? Let's look at, first I want to see what you chose. All right, I'm going to stop it. All right, most of you got it right. The answer is D, all right? This is certainly true. When you pick out a single, it's called post hoc comparisons, you have to use the Bonferroni. But you also have to do it when you calculate, you probably just didn't notice this, when you calculate, 10 at the same time, or multiple pairwise comparisons at the same time. So for sure, this is true, and I'm very glad people chose that B, but that's good. But the correct answer, the better answer is, if you had to choose one of these, is both A and B, but not C. Beforehand, you don't have to. Okay, does everybody understand that? All right. Now let's just do our last chapter. So let's go back to our notes, and I think we're going to get out early today. It's going along quickly here. Okay. So now let's look at, we did the summary, and now let's look at the next page, 187. And we're going to do a randomization test, and you're very familiar with it. It's the same idea as we already did with regression, okay? The same idea as in chapter 37. I'm just going to do it again. But it's an easy way to, I just want to look at the logic behind doing the parametric tests, which was the z test, the t test, the chi-square, all the f, versus these re-randomizations. And I think it's very clear in the ANOVA example. So you might say, how do we do we're doing a randomization test. You say, hey, but we don't have a random sample. So we really shouldn't be doing any significance tests, right? We had the whole population of Stat 100 students, all 858 students who are in the class. So what we're doing often is, and so any difference we see is significant. We have the whole population, right? But we're doing when we do these significance tests, we're wondering, hey, you're sort of imagining, is this difference big enough that it would hold up in the future? Or that it's really, what we're imagining is one of two scenarios, okay? Technically, we cannot do a significance test, but people do them all the time anyway, always. So here's the thought process. Picture one of these two scenarios. So the first scenario, this that we're using, and this is what ANOVA does. This is the parametric test using, the F and chi-squared. You imagine a large population of all possible 100 students, from which our 858 students were randomly drawn. They weren't randomly drawn, but that's what we're imagining. The null is that there's no real difference between the mean group attitudes in this wider imaginary population. And we compute an F or chi-square statistic and look at its sampling distribution under the null. And that is okay to do if you really think that the class is typical, very typical of this wider population. So people do that. But there's another way, and then you have to have all these assumptions about the wider population and the distribution of your errors. But there's another way to do it, and that is the re-randomization test. And that says you imagine a randomized experiment. Again, it's imaginary. It's an imaginary randomized experiment. And the null says that knowing which ethnic group someone is in, this is what the null says, tells you nothing about the person's attitude toward gay marriage. That's what we're saying. That's the null. We know that. So if this were true, I could randomly assign the ratings, everybody's ratings, all 858 ratings, and randomly distribute them among the 5 groups. And it wouldn't be surprising at all to get the differences that we get, okay, in our sample, just by random luck. So if I just shook up all took 858 ratings, paying no attention to ethnicity, and then randomly divided them into 5 groups, how likely would it be to see these kind of differences? That's what the re-randomization test does. It's okay? So we can simulate this doing the experiment on the computer, just like we did for regression. So this is how you do this non-parametric. It makes no assumptions about any wider population or distributions of errors. It makes no assumptions about, doesn't use the central limit theorem and all the theoretical distributions that we've learned about, the normal distribution, all that. It's just doing an experiment and randomly dividing it and doing it over and over again and making our own empirical distribution and calculating a p-value that way. So this is the re-randomization test. And I think it's very useful these days with the computer power we have to be able to do this, to be able to figure out what the analogous randomized experiment would be and simulate it. And that's done all the time. It's very, very useful because the computer does it in a flash. Okay? So ANOVA assumes this first one and requires all those assumptions. All those assumptions are because we're imagining this scenario, right? And if the assumptions don't hold, then these F and chi-square tests really aren't valid. So it's always good to try to know how to do it this way too, as to check the two, compare. Just have a tool chest of ways. Statistics, I say over and over again, is just a bunch of tools, and just see which none of them fit exactly. So which situation, I don't know, some might find this more intuitively appealing. Some might find that, but this depends on a lot of assumptions, okay? And the re-randomization test just enacts this. It does a simulation. It's like you could explain it to, a junior high school kid, or you wouldn't have to teach them all about statistics to do this. It has a huge advantage of simplicity. And so it means, and you don't need assumptions, and it's easy to understand. So instead of computing a test statistic, when you do this, by estimating standard errors, assuming theoretical underlying normal distributions, that's what we're doing, like the F and the T stats do. You have to assume these normal distributions, or large enough samples that the central limit theorem kicks in, and that's when we can do the chi-square and z-test. We just use computer simulations, take advantage of the computer making these calculations so quickly. This is just beautiful, and you can see what's happening to produce randomization distributions, sampling distributions, and compute p-values from those empirical distributions rather than theoretical ones. We have to learn to really understand this, you really have to learn a lot of math too, and that's what you're going to be doing in 400 and 410 is learning a lot about the theoretical distributions that will help your understanding. I'm just giving you a seat of the pants understanding about them. But there's a lot to learn when you do it this way, and then it's always violated. Whereas this way, this is becoming way more useful with, being able to program computers to do these simulations, and that's what we should do. We should do some kind of simulations on our bonus problems. It's really easy to do, and it's so easy to understand. So I love this way. And there's other similar tests, I don't know if you're familiar, that you'll hear a lot about, called things like jackknife, bootstrap. Huge amount of these computer simulated distributions that it's fun to learn, easy to learn, and I really encourage you to do it. And they all depend on imagining something like this. Okay, so that said, let's look at it. All right, so it's just one page, and it's very easy to understand. Okay, and it's the same idea, just to remember where to look for it as for regression. So that was in as chapter, 37. It's exactly the same thing. So let's just think about it. So, all right. So we had this data set. There were two variables. They responded. Ethnicity, they answered students, 858 students, said what ethnicity they were, and gave their opinions about gay marriage. Okay? And if you want to look at it here, we can look at it. It's from the spring. I strongly encourage you to look at it. Spring 2014 combined survey 2. Okay? And this is what we got. And the question is, these differences that we got in ratings, this is the sample sizes for each, are they real? Do they reflect some real difference? Or is it just due to the luck of the draw? So we got this correlation coefficient right here of almost 0.2 between, what does this mean? Remember, correlation is just between two sets of numbers. This is between the actual ratings and what we predict from our model. Our model would predict for whites. For all the whites, we'd predict what? It's like stereotyping. ANOVA's like stereotyping. For all the whites, we'd say, hey, you're like the average of all the whites. For all the blacks, you're like the average of all the blacks. Our best prediction. For all the Hispanics, And does that stereotype hold up at all? That what group you're in, for some reason, gives you you can predict something about that, about your attitude. Okay? So, we're going to test whether there's any validity to that. So let's test the null using the re-randomization test. So the null is that you can't predict anything knowing somebody's ethnicity, that R is 0. All the means are the same in the population. There's just random chance differences. And here's our alternative. And so here's how you're going to think about it. If there really was no difference, what could we do? We could take each one of your ratings, 858, every student had a rating. We could expect to see any of them randomly associated with any of the groups. In other words, we take those ratings and randomly assign them to each of the 5 ethnic groups without replacement. We'd randomly divide our sample into 5 groups by number. So we could do, like, for example, randomly choose the first 448 ratings and just assign them here, right? Assign them to be white. And then take the next 84 and assign them to be black, and then compute the averages between all of them, right? Get the averages, and then do compute the correlation coefficient, right here between our predicted based on group membership and their actual, right? And then we do it over and over and over again. And here we did 1,000 of these, okay? And here is our observed. This is what we actually got. And here's a histogram of the 1,000 R's that we computed. And none of the randomizations, none of them even get close to that. So that our p-value, our empirical p-value is right here p is equal to 0% because 0% of this empirical histogram, this is our empirical sampling distribution of R under the null, because 0% of the histogram is beyond our sample, our actual sample R that we got. So that's really rare to get by chance. It's really, really rare. We did it how many times? 1,000 times, and we never got one. You know, of course, if that doesn't. So let's do it on the computer, and you can see. And you can try it yourself. So we're going to go to the computer, and let's just get rid of this and look at it. Okay, so I pulled it up here, and this is exactly what I showed you. Here's all your pairwise comparisons, etc. You can look at this. Now how do we do the re-randomization? You click here. We're going to do a re-randomization. And right away, look how fast. 1,000 randomizations. And there's our R, right? And in 1,000, we didn't get anything. And you can do more re-randomizations. See. You can see if anything shows up. I mean, if you went out to more decimal places, we might see something eventually. But it's very, very rare that we're going to get one. We can do 100,000. We're going to get a smoother curve. Let's do 100,000. And you'll see the curve is a lot smoother. And it looks like I can see tiny little dots. There might be something, but it's rounded. That there might be something, a p-value of some tiny bit. Okay? Does that make sense to people? And you can't tell. Sometimes you'll get one, don't think that, always the more randomizations you do, a p-value is going to appear. No, weird things can happen early on, and you might get it's just by the luck of the draw. You might get one earlier on, and then it would show up because it would be 1 out of 1,000 instead of 1 out of 100,000. So you would see it. So it's just hard to know. But the p-value is almost 0. And what is it? The p-value is very small here when we do our parametric test. So they agree. The p-value is almost 0 when we do the parametric tests as well. Okay? So that's the idea. And let me just make sure, because this is the last class before our review, let's just make sure that we covered all the pages, because I've been skipping around trying to explain some of this. And here's a good one that we didn't. Page 181. I just want you to read all the summaries for the exam. And on page 181, this is a very nice summary, and I didn't fill it in all the way. So just remember, so here's the ANOVA table, and let's just remember what SSB and SSW and SST are. So remember, what they are. So they're sum of squares. So this is the sum of our model, our predictions minus the overall mean. So these are like our group means minus the overall mean squared. This one is what? Errors. These are errors. So that's observed minus predicted. So that's the y's for all your points, however many points you have, minus the predicted, observed minus the predicted squared. And this is just that first step on the way to the standard deviation, right? It's just the sum of our deviations of all the y's, however many you have, from their mean. Okay? So for all of these, we're summing up y sub I, we're summing up from I equals 1 to n, however many points you have, the y sub i's. All right, so that's that. Now we have, people have been asking me a lot about this, which degrees of freedom go with which. Okay, so here's your model. Let's make the model blue. Okay, so this is your degrees of freedom for the model, and here's for your error. Okay? So you see how these degrees of freedom is how many groups in your model. This is how many parameters in your model. Okay? And these degrees of freedom are how many parameters, how many points go into your error estimate. Okay? This is like how many groups are in your model, how many group means are there that we're using in our model, how many slopes, p minus 1. This is how many points are spread around those estimates. How many S points go into the estimate, the scatter around your model, the scatter around the regression line. It's n minus g, or the scatter around the group means. So these are your errors, okay? And then, of course, when you do it, you always have, these are for your model, the degrees of freedom for your numerator. These are for your denominator, right? But when you simplify them, people get confused, because when I simplify it, this ends up here in the numerator, and this ends up in the denominator. But these are the degrees of freedom in the numerator, and these are the degrees of freedom. The numerator is the model. Okay, does everybody understand that? Nod, so I know. Do you understand that? Good, because I keep getting questions about that. All right. And so then, again, here we can use r squared or chi-squared. And I love it, this simplification. Remember, the numerator is the strength of your model. The bigger your r squared is, the more stronger your model is. This is the strength of your r's. The bigger your sample size, the more evidence you have, the stronger your model is. So that's, the bigger your statistic is. I'll give you a little, I think I'm going to write a little summary up of this so you understand that. But what else? So that's the idea. Okay? And just you need to know these. And also this, whenever you're doing those Z or T tests, or, you know, the number of parameters is the number of groups. And then use N, you use, you know it all. Now I'm going to ramble. I got to stop myself. Ellen cut off. Okay? So any questions? All right. Well, please come in for help. And next week, we're going to have office hours on Monday and Tuesday. And come in if you need any help. And don't hesitate to email me. And I'll be sending you my usual email about how to study for this exam. I feel like a coach ahead of time. I really want you to succeed. And I know this is difficult material, so I'm going to try to give you as much help as I can. Okay?